Serendipitously in 2007, I accidentally brought a culture of Paratanitarsus into the lab, and it proliferated. When we ran toxicity tests with it, we had a lot of stochasticity, and we thought some of that was emergence, but some of that might also have been a density-dependent effect. You might remember this graph from freshman ecology as well. You can imagine those as two different population growth curves. And on the left, we have a faster growing, perhaps healthier population, but it still hits the same carrying capacity, the point where it levels off. You might remember that as K. And then here in red, we see a slower growing, perhaps less healthy population. But if we run that experiment for too long, we won't see a difference between those two populations. That's an example of density dependence in tox tests. To avoid density dependence, we chose very, very large vessels for Paratanitarsus, and we ran it for many, many generations. Only the bottom few centimeters are actually filled with water. The rest is for adult habitat. Underneath the water level is an angled floor with a bubble lifter that circulates water. A photoanalysis system devised by Matt Bolerjack on the left here let us know if we were getting near density dependence, and once we observed that, we would end the experiment. Running the experiment longer got rid of a lot of that stochasticity, and having the photoanalysis to know how long we could run it prevented the density dependence. So these experiments in 2019 and 2020 were about 5 to 6 months long. The EC20 in the first experiment was 11.5. We're still picking the one from 2020, but we're on track to be at approximately 11.5 micrograms per liter zinc in 35 milligrams per liter hardness. Yes, that is surprisingly low. Well, as the SETAC November 1st deadline for uploading your presentation passed, I was still struggling to get my sound quality audible. So, although I failed to be a part of SETAC, I still created this talk, and I guess this liberates me to spend a couple more minutes talking about algae. I know that's not an invertebrate, and this special discussion is about invertebrates, but this is a great example of why community exposures are sometimes more important than single species exposures. When studying algae, when is algae ever a single species? It's almost always a community in either the form of periphyton or phytoplankton. Real quickly, I want to introduce you to the experimental methods associated with this study. Here you see where we grow our algae. Now, we can mail order algae after we bleach the lab, and we do fine with one strain. Or we can go to the field and collect rocks with periphyton on it and bring back communities of algae. And we can grow them on these nice little tiles if we want, or we can put that substrate from the field on into these growing chambers that you see on the far right and far left. Now this is just your run-of-the-mill gravity-fed cereal diluter. So we have high toxicants on one side, and it slowly dilutes and delivers those to the experimental units in a flow-through system. Nothing special about it other than it's stainless, so I can use organics. And here we see our experimental units. These are small little experimental streams that recirculate water with bubble lifters, so there's no pumps involved. And it holds porcelain tiles unglazed and allows algae to grow on those. So we have nice little periphyton cultures that are getting flow-through systems, but also have a temperature-controlled recirculating pumpless system. Now, in these toxic algal bloom experiments, we measured many endpoints, including physiological endpoints using a pulse amplitude modulated fluorimeter, coarse taxonomy using a benthotorch, and traditional taxonomy under a microscope, as well as other endpoints. But really, I'm just going to focus on the coarse taxonomy endpoints. It's really easy to see those results. Okay, now most traditional tox tests just look at survival. So we could mail order algae, grow them on tiles, as you see on the left, put them in the streams, And then from the toxicant eluter on the right, deliver the toxicant. And after, those biologically important durations of 4 days or 30 days, we could see what survived. So that is one approach, but I don't feel it's appropriate for toxic algal blooms. If we instead took water from our algal cultures and delivered it upstream of our flow through toxicant eluter, we're now not analyzing survival of the periphyton, but we're seeing how quickly it can colonize those bare tiles in our experimental streams here in the middle. And if rather than mail ordering a single species of algae, we sent grad students all throughout the state of Colorado and collected periphyton covered rocks and put those in our algal growing chambers here on the left, well, now we get to see competition between those taxonomic groups. Now, the results were really interesting, and it really shows that a single species test with mail-ordered organisms, it might not be the same responses you would get with the community of algae that you field collected. Now, in this study, we took the algicide copper sulfate, really common out here in the West, to knock down toxic algal blooms. And we exposed it at different concentrations. What I want you just to do, though, is have yellow be the high, and have this purple and blue be your control and your low treatment. If we had exposed cyanobacteria, shown up here at the upper left, alone, not in a community, I predict that cyanobacteria would have been tolerant at all concentrations, and we would see all those lines parallel each other at the top. But because they were competing with diatoms and green algae, we see that cyanobacteria were outcompeted at low concentrations, this dark purple and dark blue. And as time passes, cyanobacteria populations decrease in those controls. Now, if we look down here at the diatoms in the green, and I should point out that diatoms are really good fish food, cyanobacteria is what causes toxic algal blooms. At high concentrations, indeed, diatoms in green are knocked out. But at low concentrations, they're increasing, and they're fighting off the growth of cyanobacteria, which is the cause of toxic algal blooms. And what's funny is copper sulfate is what we're using to knock down cyanobacteria to prevent toxic algal blooms. So a really interesting response that we only would get with field-collected communities. The world is starting to make progress and starting to use biomonitoring data to derive safe water quality thresholds. But for the most part, biomonitoring has been ignored, mostly because it's not experimental and we don't know how to include mathematically observations from the field. Now, mesocosm experiments, on the other hand, are true experiments. We can get really great data that would inform our policies experimentally through mesocosm experiments. But for some reason, they're not readily incorporated into the derivation of standards in the United States. And we could have a whole panel discussion as to why that is. And I'm hoping in the years to come, as we update this 1985 protocol, we come up with ways to incorporate data from mesocosm experiments, and that these guidelines are flexible so that scientists can be creative in honing the right tools to study community responses. Because we don't want to get stuck with another blunt hammer. Now, use of field-collected organisms in traditional laboratory experiments or untraditional laboratory experiments should be more common in the literature, especially to test hypotheses formed after analyzing mesocosm and biomonitoring studies. I think the biggest hang-up is the risk and the cost. If you think about a private sector firm, they cannot promise that a field-collected organism will be available, or that the experiment will meet the criteria of ASTM guidelines. So, in the case of academics as well, you wouldn't want to let your master's students struggle with the unknowns and risks associated with field-collected organisms. As I will attest to, this added realism can slow graduation by many, many years. Now, field-collected organisms in a single species test can improve environmental realism, but it can also lead to bias for the reasons I discussed earlier in the talk. It's only easy to find large, ubiquitous organisms. Taxonomy is really, really hard until they're old. And many require complex habitat and aquaculture techniques and apparati. So scientists are constantly asking themselves, are we really testing the most sensitive life stages, or are we failing to test the most sensitive species when we rely on large, ubiquitous field-collected organisms? I have no evidence, but I fear that peer review might also be blocking studies that use field-collected organisms at early life classes, because many of the ASTM and EPA guidelines for acceptable data are not compatible with useful experimental methods and test organisms from field-collected species at a small size class. I talked about a couple of those in this talk today. If not precluding such studies, it is at least discouraging to the scientists to consider running such studies. So ASTM and EPA guidelines for acceptable data need to be modernized and made to be more flexible so we're not stuck again with the same old hammer. I hope that some of the methods I presented in the previous slides help you be creative in finding ecologically relevant ways to incorporate field-collected organisms in your laboratory studies. I want to send a big apology to SETAC for failing to upload this by the November 1st deadline. I just really was struggling with some of the technological difficulties of this modern era. I really want to thank all the people on this closing slide, as well as many others who have helped with these experiments in years past. I encourage you to contact me if you have questions or comments about this talk. Thank you very much for your time, and I'm sorry I ran over.